So, good morning. Um, Today I have non-oxide refractories, carbon, silicon carbide, and silicon nitride. They're the three primary non-oxide materials that are used for refractories. And next week we'll talk about carbon matrix refractories, the composites. So this section on carbon is a bit of a background. So for any one of these non-oxides, we'll do raw materials, phase diagrams, processing, the resultant microstructure, and some key properties. So coke is just carbonized coal or carbonized petroleum residue. So the coke is from coal, it's metallurgical coke, and metallurgical coke has about 8 to 10 weight percent ash. The ash is primarily a clay, and there's also sulfur, maybe 1 to 3 weight percent sulfur. The petroleum coke, those residues are higher purity, so there's a lower impurity content. And then graphite can either be natural or artificial. Natural graphite is a mined product. It can have very large plate-like crystals, and the ash content is variable depending on the mine, anywhere from 2 to 35 weight percent ash. And then artificial graphite, you start out with a metallurgical coke or petroleum coke, and you heat it to high temperature. So you graphitize the coke, and these temperatures are quite high, over 2,500 degrees C. So it takes a high temperature to graphitize the amorphous coke products, whether it's metallurgical coke or petroleum coke. This is a natural graphite mine. It's an open pit mine. So it's mined as an open surface. And China, Madagascar, Sri Lanka, and Canada are the main sources of flake graphite. And the fixed carbon content, about 90, 91, 87, and 95% by weight of carbon. There's some volatile materials, usually less than 1 or 2%. And then the ash content is the balance, and they range from about 7 to 11% ash. The natural flake graphites, the graphite flakes can be fairly large, and they have an advantage. They have a little bit better oxidation resistance than smaller flakes or amorphous carbon. So these are the same four sources: China, Madagascar, Sri Lanka, and Canada. And this is the ash content, the chemistry of the ash content. So you see there's quite a bit of silica and alumina, and then there's also some iron oxide. So you have iron oxide and clay as the primary impurities, and then you also have TiO2, CaO, MgO, and then the alkalis, K2O and Na2O. But alumina, silicon, and iron oxides are the primary impurities in the ash. So the natural flake graphite has to be purified. So I showed a picture of an open pit mine. That material is crushed to a particle size less than 5 millimeters, and then it goes through a flotation process. So after the flotation process, it's about 96 weight percent carbon. That could be the final product, so it would be screened into sizes, and then it would end up as the final product, or it can go through other processes to refine it. So you can do a reflotation process to get it a little more pure. You can do a chemical purification where you use perhaps an acid to etch away the impurities. So you can get up to about 99.98% carbon. And you can do a chemical thermal purification. So that the chemical would dissolve the impurities and then the thermal would evaporate impurities. So you can get up to 99.99% carbon. And these materials can be ground into different sizes. So you end up with a final product between 96% carbon and almost 100% carbon, depending on how you treat it. Carbon black is another raw material sometimes used in refractories, maybe in a castable, maybe in a composite refractory. So carbon black is made from pyrolysis of hydrocarbon gases. So pyrolysis is just incomplete combustion, and you end up with a fine amorphous carbon. So methane is one possible source for pyrolysis. So methane is CH4 plus oxygen for combustion, and you end up with water plus carbon. So very fine particle size carbon, that's carbon black. Pyrolytic carbon, I just mentioned this because it's another source of carbon. This would be a high performance technical type ceramic. It would not be a way to make carbon for a refractory. But basically, you crack a hydrocarbon gas on a hot substrate. So it's a chemical vapor deposition product. And the carbon tends to grow in large columnar crystals perpendicular to the substrate. So it's anisotropic. And you can also crack methane. So it gives off a hydrogen gas plus carbon. And it's most likely going to be in graphite, these columnar type graphite crystals on a substrate. So carbon black can be used to make refractories. This pyrolytic carbon, I just mentioned it to illustrate another way of making carbon or graphite. So coke is amorphous. It's maybe 1.8 to 2 grams per cubic centimeter. The 6-member hexagonal rings are disordered. And so it's poorly crystalline and it has small crystallite size. So coke is amorphous, poorly crystallized, disordered hexagonal rings of small size. Graphite is well crystallized, it's hexagonal, it has a layer structure, it's denser, 2.25 grams per cubic centimeter. And these layers have a stacking sequence, and I'll show that in a minute. The sequence is ABAB, so the layers repeat. The layers are the basal planes, so parallel to the basal planes in these hexagonal rings, there's very strong covalent bonding, but perpendicular to these basal planes, the bonding is very weak. It's van der Waals bonds. So it's a layer structure, so the properties are directional. So properties like thermal expansion, thermal conductivity, strength, electrical conductivity are going to be a function of direction. So this could be a block you start out with, and it's in a temperature gradient. Basically, on this diagram, goes from about 500 to 2500 degrees C. So at low temperatures, you have very disorganized structure. There's some 6-member rings, some rings of lower quantity of carbon atoms. It's very disorganized, it's amorphous, but as you heat it up to these higher temperatures, you get this hexagonal type graphite structure, so it becomes well crystallized. And if you do the X-ray diffraction as a function of temperature, there's peak sharpening. So there's these different peaks for graphite, and as you increase the temperature, you increase the graphite content, and the X-ray diffraction peaks increase in intensity. So again, at low temperature heat treatment, it's a very amorphous, disorganized structure. As you increase the heating temperature, you realize the graphite type structure. So this is graphite. The black circles are the carbon atoms. They're hexagonal, 6-member rings. So in this layer, the basal plane, you have the very strong covalent bonds. Then perpendicular to the basal plane is the C direction. These bonds are very weak. So the properties are going to be very directional. So carbonized coke is amorphous. When you graphitize it, you end up with graphite. You have an ordered crystalline structure. In either case, carbon does not melt. It basically decomposes or evaporates at temperatures greater than 3,500 degrees C. So it's stable to a high temperature, and then it sublimes above 3,500 degrees C. So how do you make either amorphous carbon or artificial graphite? You start out with coke, and that material is crushed and screened, and then remix into the right particle size distribution. And these are going to be basically for particle size distributions that give maximum density. The binder for coke is going to be pitch or a phenolic resin. So either one of these sources for a binder, pitch or phenolic resin, they have high carbon yield when they go through the pyrolysis process. So they each yield about 50% carbon when they are pyrolyzed. So they add carbon to the product. They're also the binder. Phenolic resins are most common right now. Pitch was used in the past. It has issues concerning health issues, concerning it's a source for cancer issues. So pitch is less safe than the phenolic resin. So phenolic resins are more common today. So in the mixing, after mixing with the binders, it's a low temperature process. If it's pitch, phenolic resins can be mixed at room temperature. Pitch is mixed slightly warm. They can be extruded or pressed. And these are usually extruded or pressed into fairly large blocks. So after extrusion or pressing, it goes to a baking furnace. And the baking furnace is maybe 750 to 1,000 degrees C. And you hold it for as long as 4 to 6 weeks. That converts the binder to additional carbon. But at these temperatures, they're pretty low. So you have an amorphous carbon. After the baking furnace, you can send it to a graphitizing furnace, or you can add pitch or resin by an infiltration process. So there's porosity here. You can fill the porosity. You basically take the block of amorphous carbon, put it under a vacuum, and infiltrate the pores with more pitch or resin. Go back into the baking furnace and convert that pitch or resin to additional carbon, and you can repeat that as many times as you want to get it rid of the porosity, make it a denser product. So from the baking furnace, it can go to a graphitizing furnace. So these are much higher temperatures, 2,600 to 3,000 degrees C. It takes 4 to 6 weeks to make graphite. So that's an artificial graphite product. So in either case, amorphous carbon or artificial graphite, there's a machining step. So when you make artificial graphite, you're putting these graphite blocks in what's known as an Atchison furnace. So there's a refractory foundation. And these are the large blocks, these rectangular darker gray regions are the blocks. They sit on top of the refractory foundation. There's a filler that surrounds these blocks that's resistance heated, so it's a carbon refractory type filler. There's a carbon or graphite electrode on each side of this furnace and a power supply. So you do a resistance heating of this filler, and eventually these blocks are also conductive. So it's a resistance heated furnace, and like I said, it goes to a high temperature, and after a long time, these blocks are converted to graphite. So when you process a product based on carbon or graphite, there's a couple possibilities. This is a graphite clay or ceramic mixture. This has been used for a long time to make crucibles. So you add clay, it's a processing aid, but it also protects the graphite from oxidation. So carbon or graphite has an oxidation issue. The clay basically coats the graphite and is a barrier to oxidation. Graphite is a high strength material. It has low thermal expansion, high thermal conductivity, so that leads to good thermal shock resistance. So you start out with graphite and clay, you mix that. The binder again is going to be either pitch or phenolic resin. Years ago, primarily pitch was used. That use of pitch has decreased over the years, and it's now a phenolic resin. And then after mixing, you can extrude or press products, and it goes through a baking oven to pyrolyze the binder, and then it's machined. So the clay is there just to protect the graphite and as a aid in forming. So the properties depend on the degree of crystallinity of the carbon, how much graphite is actually there, and the orientation of the crystalline units that are formed. So you can have a wide range of properties depending on how you process this. So here are small crystals of graphite that are aligned during the processing. And then here's a more random arrangement. So these properties on the left-hand side are going to be a function of direction or anisotropic. These are not going to be a function of direction. They're going to be isotropic. So thermal conductivity is high in the basal plane, low in the C direction, perpendicular to the basal plane. So if you have a product that maybe is extruded or pressed, the graphite crystals will align like this. So in the horizontal direction, that'll be the direction of high thermal conductivity. And then in the vertical direction, that'll be the direction of low thermal conductivity. Then thermal expansion is low in the basal plane, but high in the C direction, which is again perpendicular to the basal plane. So in the horizontal direction here, the strong covalent bonding is going to give low thermal expansion. And then in the vertical direction, in a material that looks like this, you'll have a high thermal expansion. That difference in thermal expansion is substantial in those two directions. It's quite large. So the thermal expansion mismatch in a material like this is going to create stresses. Stresses are going to lead to microcrack formation. So in materials that have high graphite content, usually you're going to end up with some type of microcrack situation. And graphite even amorphous carbon has hot strength. As long as it's reducing or not oxidizing atmosphere, the strength of these materials is quite high. I mentioned thermal shock. Anytime you have a material with high thermal conductivity, low thermal expansion, it's hard to build up stresses when you have a temperature gradient. So because of the high conductivity and low expansion, you're going to have very good thermal shock resistance. And I have a course where we talk about properties, and corrosion is one of those properties. If a molten metal or a molten slag or molten glass does not wet a material, corrosion is really limited. If it doesn't wet, it limits the reaction that can take place. So graphite in contact with a slag or a molten metal, those molten materials do not wet the graphite. So the corrosion resistance is good because of poor wetting by molten metals, slags, and glasses, and so on. So good thermal shock resistance, good corrosion resistance, but the drawback on these materials is the oxidation resistance. So again, there's always seems to be a trade-off on any one of these refractory type materials. So if you have an oxidizing atmosphere, oxygen, O2, or CO2 present, you take the temperature up to higher than 600 degrees C, the carbon is going to oxidize. The flake graphite, the larger the flakes, you get a little bit of better oxidation resistance compared to the amorphous carbon. So you have to protect these materials. Surface and body glazes. We mentioned a clay graphite mixture. And actually, if there's a lot of ash in the material, well, that will basically melt at higher temperatures to form a glass and also form an oxidation barrier. So adding a glaze on the surface using clay in the matrix or the ash that's contained in the carbon can all form oxidation barriers. And when we talk about a carbon matrix in a composite material, there's a variety of ways to protect the carbon from oxidizing. So we'll talk about that next week. So here's some basic properties. This is a standard metallurgical coke. This is amorphous. This is a calcined coal, anthracite. This is a metallurgical coke enriched with graphite. This is a high purity, high graphite content blast furnace material. And this is an electrographite used in for electrodes. So this is even another high purity material. So the bulk densities are all about 1.5, 1.6. The porosities, and that's in grams per cubic centimeter. The porosities in percent are all around 15 to 20%. And you can see the coal crushing strengths are rather decent, 2,000 to about 9,000 PSI. So the conductivity is going to depend on the graphite content. So this is thermal conductivity, and the units are BTU, inches per hour, foot squared, degrees F. There's various other units for thermal conductivity, but these are in the BTU units. And then the conductivity here is shown for 400, 750, 1100, and 1500 degrees F. So these are around 30 to 40 for the metallurgical coke. The coal, the anthracite is slightly higher, about 40 to 50. And then as you add graphite to the metallurgical coke, you can see the conductivity going up. It's around 100. And then the higher conductivity blast furnace material, which has a higher graphite content, that is maybe 200 to 240. And then the high purity material, um, highly graphitized, starts out at about 800 and drops to about 400. And then the ash contents, these last two materials are pretty high purity. The ash content's only about 1. And then these other materials are 3, 5.5, and 8. And that's in percent. And we'll do the same thing for silicon carbide, the raw materials, phase relationships, how they're made, the different kinds of microstructures that you can make, and then a couple of important properties. So silicon carbide is a synthetic material, and you basically heat a mixture of coke, which is your carbon source, silica, and sawdust. So 3 components. You electrically resistance heat it. So the resistance heating produces temperatures about 2200 degrees C. At those temperatures, the silica reacts with the carbon, is reduced to silicon, and then the carbon reacts with the silicon to form silicon carbide. And as you form more silicon carbide in this furnace, that also becomes an electrical conductor at high temperatures. The reason why you add sawdust, it just burns off and leaves porosity that allows for gases to escape. So the reaction is silica SiO2 plus carbon, forming silicon carbide plus carbon monoxide gas, which comes off through the porosity. So these are rather long, large furnaces, similar to the Atchison type furnace. It's basically the same as an Atchison type furnace. There are 2 basic forms, crystalline forms of silicon carbide, beta silicon carbide and alpha silicon carbide. So a beta silicon carbide is the low temperature form. It's cubic, and it's about 3.2 grams per cubic centimeter, and it's stable to about 1900 degrees C. The alpha form is the same density, about 3.2 grams per cubic centimeter, and above 1950 degrees C, it transforms to the hexagonal structure. Silicon carbide doesn't melt, but when you approach temperatures of 2400 degrees C, it dissociates or decomposes to silicon and carbon. So there's different ways of making a silicon carbide refractory. One is fire clay bonded. This is similar to the fire clay bonded carbon. So it's a dry pressing process. You basically have about 15 weight percent of fire clay. You mix it with about 85 weight percent of silicon carbide. So you have a fire clay matrix with silicon carbide grains or aggregate, and then you sinter this material at a pretty low temperature, 1300 degrees C, and the clay is converted to a combination of mullite and glass, as we already have discussed. So that's the fire clay bonded silicon carbide. There's a nitride bonded version. So you start out with 10 to 15 weight percent of a silicon powder, and then the balance 85 or 90% is the silicon carbide aggregates. So you dry press this mixture, and then you sinter it at about 1400 degrees C in a nitrogen atmosphere. So the nitrogen N2 reacts with the silicon, and that forms your silicon nitride. So again, the nitrogen converts silicon to silicon nitride. This material is useful to about 1900 degrees C. And one advantage of forming a refractory block or shape is that when you nitride it, there's very limited shrinkage. So it's kind of a nut shape forming process. There's also reaction bonded silicon carbide. Now you start out with 10 to 28% carbon powder, and then the balance 80 to 90% is the silicon carbide aggregates. So fine carbon, and then the silicon carbide grains. So then you sinter it, heat treat it at a higher temperature in a vapor of silicon. So you're evaporating silicon in this operation. The silicon vapor penetrates the refractory and reacts with the carbon and forms silicon carbide. So the silicon vapor converts the carbon to silicon carbide. Again, this is a limited shrinkage process, so it's kind of a net shape forming process. And I'll mention these other three processes for making silicon carbide. They're not necessarily useful at all for making a refractory. They're making a high performance material and an expensive material. So hot pressing is an expensive process, and it's designed to make very dense silicon carbide materials. So silicon carbide is covalently bonded. So when you try to sinter a covalently bonded material, the atomic diffusion rates are small. And again, I have another course on sintering, and one of the main things that happens during a sintering process is atomic diffusion, and that lowers the porosity and densifies the material. But it's hard to sinter a covalently bonded material because of the low atomic diffusion because of the strong bonding. So you can hot press this material. You apply pressure at high temperatures. So the pressure aids in the densification process. You can have a pyrolytic graphite, which is a vapor deposited material. So you're putting down a coating on a substrate. Methyl dichlorosilane is a possible raw material. So this gas hits the hot substrate and decomposes and forms silicon carbide. And then you can make silicon carbide fibers. Polycarbosilane is a source or a precursor for silicon carbide. So you spin fibers from polycarbosilane, basically making polymer type fibers. You go through a pyrolysis process, decompose the polycarbosilane into silicon carbide. So you end up with fibers 10 microns, 20 microns in diameter. So hot pressing, you can only make simple shapes like plates, maybe cylinders. It's very expensive, but it makes a very dense material. So none of these processes are going to provide useful materials to make a refractory. Actually, it would be nice to add silicon carbide fibers in some cases, but these fibers are extremely expensive. The microstructure for a fire clay bonded material, I have a schematic diagram here. So during the firing process, the silicon carbide to some extent oxidizes. So these are silicon carbide particles. The black is still silicon carbide. The ring around it, the light colored ring, this is not drawn to scale. It's a very thin layer, but you oxidize the silicon carbide surface and it forms SiO2. So now the silicon carbide oxidizes during a sintering process. It's an oxidizing sintering process in an air atmosphere. You form this thin silica layer on the surface of the silicon carbide. And then when you have clay, your aluminosilicate matrix, you're going to end up with mullite and glass. And that forms a very good bond with the silica layer. So you have oxidized silicon carbide grains with the SiO2 layer and your clay matrix of mullite and glass. So these white, the brightest white, they're all angular, so they're crushed silicon carbide. So that's your silicon carbide aggregates. Here's a large silicon carbide, and then you can see the smaller pieces, and there's even much finer pieces in the matrix. This gray color, there's a lighter gray color for the clay and a little bit darker gray color for the pores. Here's a large pore. So you can see the clay, the mixture of mullite and glass bonding the silicon carbide aggregates. And there's quite a bit of porosity in this one. This is 50 microns, and this is also 50 microns, but it's a higher magnification. So you can see the silicon carbide grains, the brightest white, angular type pieces. And then you can see your clay matrix. And then these are pores. So the clay is bonding to the silicon carbide and is forming the matrix, holding the refractory together. And again, this clay is an oxidation barrier protecting the silicon carbide. The nitride bonded material, you're basically ending up with silicon carbide grains in the silicon nitride matrix. So a schematic diagram, the black circles are the silicon carbide grains, and then your in situ silicon nitride, the gray area is the matrix. So this is, the matrix starts out as silicon metal, you nitride it to silicon nitride. So the bright angular particles again are the silicon carbide. The very dark, small regions are the porosity. And then the lighter gray is the matrix of silicon nitride, but there's also fine silicon carbide particles in the matrix. That's the way it was processed. So you have angular crushed silicon carbide aggregate in a matrix of finer silicon carbide and the in situ silicon nitride. This is one that I actually looked at. This is a 35x micrograph of a nitride bonded silicon carbide. So when you do the EDS analysis, you have silicon about 54 weight percent, carbon about 35 weight percent, and nitrogen about 8 weight percent. And then you have aluminum, iron, and calcium impurities. So these large gray aggregates are the silicon carbide. When you do the chemistry, they're about 70% silicon and 30% carbon. That's silicon carbide. The darker black, again, is the porosity. So you can easily see the matrix here between all the silicon carbide aggregates. You can pick out finer pieces of silicon carbide. And then if you analyze the matrix region, it's about 58% silicon, 19% carbon, and 16% nitrogen. So it's a mixture of fine silicon carbide from the silicon and carbon, and the silicon and nitride is the silicon nitride, the silicon and nitrogen. So if you map this is silicon in blue. The silicon in silicon carbide shows up very distinctly. So you can see the coarser aggregates, and then you can see the very fine aggregates. So that's the distribution of silicon. The nitrogen here is in the red-orange color. There's a void area here and so on. That's where the silicon carbide aggregates are. So the nitrogen shows up in the matrix, and it doesn't show up very brightly here, but it's in the matrix. That's where the silicon nitride is concentrated. The aluminum impurity in this pink purple type color is also concentrated in the matrix. It is actually a small, it shows up very bright here, but it's a small impurity concentration. But it is isolated, tends to be isolated in the matrix also. And then the material that's a reaction bonded, you're going to have silicon carbide grains in a silicon carbide and silicon matrix. So you have your coarser silicon carbide grains, the black circles here. And in this process, you start out with silicon metal with the coarse silicon carbide grains, and you vaporize silicon, and it infiltrates and reacts with the carbon. I'm sorry, you start out with the silicon carbide grains and a carbon matrix. You infiltrate the carbon matrix with silicon, and you have an in situ silicon carbide matrix, which is the gray region. But it's not really a complete process. You have these small white circles are residual silicon metal. So you end up with coarser silicon carbide grains and a silicon carbide matrix and some residual silicon metal. So in this micrograph, the silicon carbide are the darker gray aggregates. So you can see their crushed product, they're all angular. Very dark circles are pores. And then the silicon is the bright phase here. And in between that is also the in situ silicon carbide. So this one has quite a bit of residual silicon metal. And I just mentioned pyrolytic silicon carbide and the silicon carbide fibers. When you crack a gas on a substrate, you're going to end up with crystals that grow from the substrate or perpendicular to the substrate. So they can be fine or large columnar crystals. It just depends on the processing conditions. And then the silicon carbide fibers are mostly silicon carbide. There may be a small amount of silica or fine carbon present also. Again, these are more for high performance technical ceramics, and they're expensive raw materials. So silicon carbide is covalently bonded. It is high strength and high creep resistance. Again, the low atomic mobility prevents creep from a diffusion type process. So it's high strength, high creep resistance because of the strong bonding. Strong bonding gives low thermal expansion. It has high thermal conductivity. So it has pretty good thermal shock resistance. Again, low expansion, high conductivity, prevent thermal stresses, and enhance the thermal shock resistance. Very hard, strong material. Abrasion resistance is good. It has good corrosion resistance as long as whatever it's in contact with is non-oxidizing. And the problem with silicon carbide is at high temperatures it will oxidize. So carbon, we talked about carbon oxidizing at temperatures greater than 600 C. Silicon carbide is a little better. It'll oxidize at temperatures greater than 1,000 degrees C. And there's two different oxidation mechanisms. One is passive oxidation and one is active oxidation. So this is passive oxidation, and that occurs when you have high oxygen partial pressures. That would be an air atmosphere. The partial pressure of oxygen in air is about 0.2. So when you have passive oxidation, the silicon carbide reacts with oxygen, forms SiO2, and a CO2 gas comes off. So here's your silicon carbide material below this line. This layer is your oxidized SiO2 layer, and then your CO2 comes off. So the SiO2 layer is a barrier to further oxidation. So you develop a protective silica layer, it slows the oxidation. So the oxidation process is then controlled by how fast the oxygen can diffuse through the silica layer and react with the silicon carbide. As the layer gets thick, the kinetics become parabolic. So the thicker the layer, the slower the oxidation rate. The other possibility is active oxidation. So if you have very low oxygen partial pressure, you don't have enough oxygen present to form SiO2. So in this case, oxygen plus silicon carbide forms an SiO gas and CO gas. So here's your silicon carbide material. It's reacting with oxygen. CO is coming off, SiO is coming off. There's no protective layer. So you don't have enough oxygen to form the silica layer, and oxidation just continues in this process until all the silicon carbide is depleted. So the kinetics here are simply linear. There's no diffusion barrier to convert it to a parabolic type kinetic situation. So silicon carbide has a lot of good properties, but poor oxidation resistance. So a brief data sheet, a hot pressed material, a clay bonded material, a nitride bonded, and 2 reaction bonded materials. The hot press has the highest density, 3.15 and grams per cubic centimeter. Clay and nitride bonded have porosity. So if you look at the porosity, hot pressing gets you close to 0. Clay and nitride bonded are typical, 16 or 18%. Reaction bonded is also low porosity, so the densities are pretty high, 3.1 and 3. So when you have dense materials with low porosity, this is the bending strength. This is 78,000 PSI. This is 56,000. This is 36,000. So these are very high bend strengths. And then the clay and nitride bonded materials are still high for a refractory material, but much lower than the fully dense materials. And then in these BTU units, the thermal conductivities, the first 4 are at room temperature. This is a dense material. It's going to have a high thermal conductivity, 1400. The clay bonded and the nitride bonded are lower, 100 and 240. And the reaction bonded material here is 1,000. It's going to decrease at the higher temperature. It's down to 310. And again, I teach a course on properties that'll tell you the relationship between thermal conductivity and temperature. But for these dense refractory materials, thermal conductivity is going to decrease with temperature. The thermal expansions are pretty low, all under about 5 times 10 to the minus 6 per degree C. And this expansion is an average from 20 to 1,000 degrees C. And to keep this in perspective, MgO was about 13.5, about 3 times higher, and alumina was about 8.4, about 2 times higher. These are the maximum temperatures that you can use these materials. And then the silicon carbide and the silicon nitride content. Hot pressed was a high purity, 99% silicon carbide. This reaction bonded was 99%. This one had more impurities, 90%. The nitride bonded material, the matrix here is 25% silicon nitride, and the aggregates of silicon carbide are 75%. And the clay bonded is 85% silicon carbide, and then the balance would be their fire clay. And then the same thing for silicon nitride, the materials, the phase relationships, how they're made, what the microstructure looks like, and some properties. So silicon nitride is another synthetic material, man-made. You simply start out with silicon metal powder, you heat it in a nitrogen atmosphere, and the temperatures you heat it to are 1250 to 1400 degrees C. So the silicon metal plus N2, the nitrogen, forms silicon nitride, Si3N4. You can also heat silicon metal in an ammonia atmosphere. Same temperature range, 1250 to 1400 degrees C. So you have silicon metal plus NH3 forming Si3N4, silicon nitride, and then you have a gas coming off, hydrogen gas. So two ways to make silicon nitride. There's an alpha silicon nitride at low temperatures and a beta silicon nitride at high temperatures. So the alpha silicon nitride is in the trigonal crystal structure, and it's stable up to 1550 degrees C. It's about 3.18 grams per cubic centimeter. The beta silicon nitride is hexagonal, so it's hexagonal greater than 1550 degrees C, and it has about the same density as alpha silicon nitride. Just like silicon carbide, it doesn't have a melting point, but it decomposes at about 1900 degrees C. You can have a hot press silicon nitride, just like you can have a hot press silicon carbide. Again, silicon nitride, just like silicon carbide, is covalently bonded, low diffusion rates at high temperatures, so low densification. So you have to apply pressure at high temperatures to densify the material. You can also add a sintering aid, 5% MgO, 5% yttria. These help densify the material by forming a glassy type material at high temperatures to really aid in a densification process. Hipping is a pressure at high temperatures. So hot pressing is pressure from one direction in a mold. Hipping is pressure through an atmosphere at high temperatures, so it's pressing in all directions. So hipping is just sintering with pressure at temperatures about 1850 degrees C for silicon nitride. So these are our processes to make dense silicon nitride. These would be for high performance technical type ceramics. It is an expensive process. These methods are not useful for making refractory materials. Reaction bonded silicon nitride, you're compacting silicon metal. This can be a pressing operation, it could be an extrusion operation, it could be a slip casting process. So you simply take the silicon metal compact, you heat it in nitrogen, and the first temperature you heat it to is about 1250 degrees C. You're forming nitrogen on the surface of the silicon metal particles. So basically, you're forming a porous skeleton of silicon nitride around the silicon metal particles. So once you have this porous skeleton, you can go to a higher temperature, and that's above the melting point of silicon. So when you're above the melting point of silicon, the nitrogen reacts much faster to form silicon nitride. You form this skeleton, you trap the liquid silicon in this skeleton, and then you nitride it. So you're accelerating the nitriding process at 1450 degrees C. And this is another process where you have limited shrinkage. So it's a net shape forming type process. So for the hot press material, usually it's a fine grain size, 1 to 5 microns. So high grain size, small grain size, high density, low porosity, gives high strength materials. And if you add a centering aid like magnesia or yttria, you're going to have a phase that develops at the grain boundary that enhances the diffusion and enhances the densification. So if you add MgO, you're going to probably end up with a magnesium silicate glass. If you add yttria, you're going to end up with this compound, SiYON, and that's going to be crystalline. So the yttria would most likely give you a better performing material at high temperatures in terms of hot strength and creep resistance because you have a crystalline grain boundary phase, a high temperature crystalline grain boundary phase instead of a silicate glass. And the reaction bonded material is going to have about 10 to 20% porosity. So here's a refractory material, reaction bonded silicon nitride, about 10 to 20% porosity. The black areas are the pores, the remaining area, and you can't see anything here but silicon nitride. At this magnification, you don't see the individual crystals, but it's silicon nitride, polycrystalline silicon nitride with some porosity. So just like silicon carbide, it's a strong material at high temperatures. It's creep resistant. And then the reaction bonded or hot pressed materials that have a crystalline grain boundary are going to be even a higher hot strength and better creep resistance. The thermal expansion is low because of the covalent bonding. The thermal conductivity is relatively high, so the thermal shock resistance is good. Again, low expansion, high conductivity, give good thermal shock resistance. Just like silicon carbide, it has an oxidation issue. So above 1,000 degrees C, this material oxidizes. And again, there's a passive and an active oxidation process. So passive oxidation is a high oxygen partial pressure. That would be an air atmosphere. You develop a protective SiO2 layer, which slows down the oxidation. So Si3N4 plus O2 forms SiO2, and you have N2 gas coming off. So here's your silicon nitride material. You're forming the SiO2 layer, and you have N2 coming off. So the SiO2 layer is a barrier again to oxidation. Oxygen has to diffuse through this layer to react with the silicon nitride and oxidize it. So as this layer gets thicker and thicker, the oxidation slows down, and that gives rise to parabolic kinetics for the oxidation. And then if you have a very low oxygen partial pressure, very little oxygen present, you don't have enough oxygen to form silicon dioxide or silica. And Si3N4 plus oxygen yields an SiO gas plus N2 gas. So your Si3N4, your silicon nitride, is just going to form two gases, N2 and SiO, that are going to come off. No protective layer will be formed. So just like for silicon carbide, oxidation continues until all the silicon nitride is consumed. And that's simple linear oxidation kinetics. So both silicon carbide and silicon nitride have very good properties, except when it comes to oxidation resistance. So this is a hot press silicon nitride and two reaction bonded materials. You can see how dense the hot press material is, very low porosity. So it's about 3.3 grams per cubic centimeter at zero porosity. And then the reaction bonded materials are 2.5, 2.2 with 20 and 25% porosity. The bend strength on this hot press material is 120,000 psi, so it's very strong. But the reaction bonded materials are all also fairly strong. This one's about 43,000 and this one's about 37,000 psi. These are the conductivities in the BTU units, 270 and 70. So the hot press material is really high conductive material. And then the expansion coefficients, the average between 20 and 1,000 degrees C are only about 3. So these are pretty low. So that gives rise to the excellent thermal shock resistance. The maximum use temperatures are not that high because of the oxidation issues. 1,000, 1,100. This one claims to be 1,400. I don't know if that's possible, but that's what the claim is in the data sheet. And they're basically all silicon nitride. So that's what I have on carbon, silicon carbide, and silicon nitride. Next week are 2 lectures, all on the carbon matrix materials, the composite materials. So have a good weekend. Again, thanks for listening, and I'll see you next week.